Welcome back, guys. Last week we were mostly trying to fix issues around the switching between EL0 and EL1. And the moment we jump into the user process, for some reason we were not able to make the syscall. I mean, we were able to make the syscall, but the moment we jump into the kernel code, the tables were not there. And so initially when we jump from kmain into initially we have a lot of code in kmain and it's running in EL1 and it's working fine, and then we jump into EL0 for our user process. We do some work and then we call a syscall. We get into interrupt handler, and then from interrupt handler we try to use some kernel helpers which is supposed to work because we are in EL1 context and we should have the table entries, but for some reason it was just faulting the moment we get into the syscan handler. And it's definitely just the tables are missing, but the question was why exactly it was working initially in kmain, and the moment we get into the user process and we come back to alone, why is it not working? This was the question. And because previously when we started writing some user processes, it that things were just working fine, but the moment we right now we have our user process that uses a separate table, so we update the table registers, and this makes sense why when we come back here why it's not working. My initial guesses were that I know that for EL1 we have a separate table register, and EL0 we have a separate table register. At least that's how I assumed it. I guess last week I was debugging this. So in general, the overview is that we're still trying to write our own kernel. We have our initial MMU done, scheduler done, and a little bit of a block layer done, and a little bit of virtual file system layer. Has some upper templates ready, but overall currently we also finished with some syncing mechanisms um, for the spin lock that we can use inside the kernel context. Currently we are trying to test the mute spin lock because we have a scenario where our block layer can be accessed by multiple people, multiple user processes, and we need to sync it. So we added the spin lock. Now we want to test it from the user layer, but the moment we call the write syscall from the user layer and we jump into EL1, we get an error. I mean, we get a page fault and saying that we don't know what the fuck is this address. There's no translation for it. So I tried a lot to figure this out, but turns out the moment I turned off the stream last time, I figured it out. The issue was that I was assuming that we have two different registers. We do have two different registers, but it's not like it's getting updated. We do update the EL0 register because we have we have only one kernel context. So if we go into, let's just build it and see it in action. So if we are inside the here, and if we go to info registers, if we put info registers, where is it? It should start with T. Yeah, we have TB0 EL1, and we have TB1 EL1, I guess. uh, so yeah, we have two different registers, and the idea was that based on the upper bits of the most significant bits of the address, so let's say we access 0x8000, that does not have the upper bit set. That means automatically will use EL0's tables, and if there are upper bits set within kernel context, we'll start using the uh, TL EL1 table. So the switch was not actually based on which context we are in. It's just based on what address we are trying to access. That way, based on the address, the MMU will just directly use the table relative to it. And I fucking forgot this information. This is what cost me a whole session. And so at least now I know the issue. So now the issue is that this was already documented in some one of the previous session, that currently almost all my kernel code is in 8000, starting from 8000, which is not good, because that is a user space address. So the moment I put everything under 8000, that means I need the table entries to be inside EL0 register, and that is the whole issue, because right now when I go into a user process, now I have to update that EL0 register to the processes table, and then when I come back to kernel context, now I have to again update the EL0 with the kernel's table entries. This is just not good. I have to figure out a way to move all my code to separate location, or almost all my kernel code should lie in the address range that has the upper bit set. At least I have to think about a way to solve this in a proper way. Hi. I have to think about it to solve this in a proper way instead of just getting around it, because this has hurt me back twice already, and it's just not good. And every time I have to go back into L0, update the register, come back, update the register. It's just not good, and it's not going to be scalable for my future updates probably. So it's just better to figure out a proper way to separate my kernel code into address range, which can just be directly accessed within the kernel context, and I don't have to worry about EL0 at all inside the kernel context. Currently that is not possible. So now let's just figure out how much of code needs to be changed so that I can move everything into the address range that starts with FFF. That's the goal for today. Where is it? We have a to-do. Let's first of all review what is the exact flow that we use to jump from, from what I remember, we have the start, and we disable things, we set up the stack, we zero out the BSS, we update the vector table, we get total RAM, and then we initialize MMU. So this is where we actually enable MMU unit. And the moment we enable MMU unit, what do? We are updating the vector table again with FFFs in the top so that it will be valid address. And then what is this? No, we are just updating the value from here. And then yeah, this is where we actually set up the virtual entry point. So virtual entry is just jumping into Kmain. But what we do here is that we want to be in a virtual jail that is like everything is whatever address we will try to access should be in a table. If not, we won't be able to access it. And we have the physical range, which is starting from 8000, 8 something, and we have the virtual range that has the upper bits FFF, and it also has the same 8000. So this address in the virtual address space is mapped to the physical range of 8000. So this is identity mapping, and this is how my MMU works. So every time I try to access this address or anything in this range, yeah, this will go into the MMU unit, and MMU unit will know that this address is mapped to this, and that's where the whole table comes into play. Now my issue is that I am accessing certain addresses within kernel context that don't have FFF in the front. So if an address does not have the FFFs as the most significant bits set, that means the MMU unit will think it's a EL0 address, and it will try to look for those entries in EL0's table, and those tables won't have those address, and it will just end up in a fault. We'll get a page fault. And the simplest solution is that we are not supposed to use anything or any address range that does not have FFFs in the front within kernel context. And we have to do that now. So let's put a to do here. No, not a to do here. Here we don't have to do anything because we simply just take the virtual range that we want to jump into, and we jump. That's it. So what we want to do is that we need to, the moment we jump into Kmain, we are inside Kmain. So we can go to Kmain. Review all the code that is directly using 8000 as range without FFFs. Okay, so inside kernel we initialize UART. Maybe this is probably an issue because I don't know if UART uses UART is also using FFF as the base address, so that should be fine. And then we have some prints, and we have gneet. What the fuck is that? I think this is just enabling the interrupt handler for the CPU, because we have the normal exception handlers, which is also needs to be enabled, and we also have to enable CPU to know that we have exceptions coming, and this unit is what is going to handle what sort of exceptions can come in and what sort of exceptions do I even have to care about, things like that. And which is what's the address range for it? And the address range is FFF8 something. So, and it is being mapped to the physical. I believe so. Yeah, this is virtual and this is physical. So this layer also has it properly. Okay, let's move on. And we enable timers. What we do, we read, set, enable. That's fine. Or do they have any sort of address range? What is set to? No, address enable to. Okay, it does not seem to be doing anything interesting. Overall, we are just simply writing to registers. So I believe it is fine. We don't have to do anything here. What the fuck? Where's my keymain? The fuck is going on? Okay, and then I have my initial bitmap allocation. So what I do here is that I have my kmalloc. So that's the memory allocator for my kernel space, the EL1. And to keep track of the memory, I have a bitmap, and every bit within that map is of how many? I guess 4 KB. What? Yeah, I just allocate block. Yeah, the memory location starts from here, and this is actually a linker region. If we go to our linker, here we can see that we have set up 500. So it's every block is of around 512, and we have 512 into 1024. It's around, I guess, 1 GB. And we get this as the starting address, and we should be able to allocate 512 bytes 1000 times. And this is the end. So this entire region is being used as the used as what? Used as used just for bitmap? Why do we need that much space? That does not make sense. We use no, it's just memblock. Memblock is like we can use no, we have a max size, and we check if the max size is that. I guess max size is just 512 into 1024. I think so. Let's double check that. 512 into 1024. Yeah, because in our linker script we have allocated the memory region, and the memory region start is being used here. We can only allocate maximum of 5,24,000 bytes. That's like, I think 500K, around 500K. Okay, that's fine. So we just always return the starting address. That's fine. That's my. I have to split it. It's getting annoying. Okay, we get the starting address as this, but now I don't understand why my bitmap needs this much of bytes. What does it even store? It's just going to store, and I just say that it is allocated, and then what do I do? I call kmalloc. As soon as I have the bitmap, I can call kmalloc. Okay, let's see what is kmalloc. Kmalloc has allocate mem bddex to physical map pageable entry. Let's go through one by one. We have allocate mem, which is just going to set within the bitmap saying that this memory location is used. That is all we do. So if the size is, yeah, so every bit within this bitmap is gonna be 4 kb. So if we set one bit within this bitmap, that means we are saying that that particular 4 kb is allocated, and then we can use the arithmetic indexing just to we can make sure. Let's say if we want to know if the address 8000 is allocated, all we have to do is just divide 8000 by 4, 8000 by 4096, and then we would get the index, and we check if that index is set to 1 or 0. If it's set to 1, that means that address is being used. That's the whole logic behind this bitmaps. This is the entire thing. So we say that we have a size and we divide it by that address, and we use that as the index. And if we go into set bitmap, here for every index we also have to find a free bit. And what do we do within that? We only have total of 16,385 bits. I think that's the amount we want to support. Maybe we can write that down. This is the amount of bits we support within our bitmap array, and the index calculation is just index and bits, and if it's true or valid or not, and we check if it's free. What do? We check temp memory buffer index, and if that's index and the vector, I don't understand what the fuck this is actually. Probably we are doing some indexing to get a certain bit. Yeah, because I think the index also holds other information, so only a specific bit within that index actually means that this address is already used. So we use that, and if we actually found something, we would just return. If not, we increment the bit, and we keep repeating until we find a bit that is free, so that we can just return I. If not, we keep incrementing bits, and whenever the bit has reached 8, we just set the bit value to 0 and index to the next index, because a single index can have up to 8 bits. And so if a single bit has 8 bits, that means overall a single index can whole 8 pages of 4 KB size. Okay, even now we still don't see anything that is using the memory range 8000, so we can keep going. Oh, I fucking hate this game, man. Okay, now we just simply test if the memory location is working, and then we try to get drive info, which is actually trying to parse the DTB and get the register addresses for different devices. So this part, does it require? I think this part requires. Yeah, DTB is in range 4000 something. So yeah, probably we. But even here, I guess we are using virtual DTB base. So the original DTB base is 4000, which is the physical address. But we have a virtual DTB base, which is just FFF854 something. And this address is mapped to this physical. So whenever we try to reach this, MMU will know that we are reaching something in this range. So this is also fine. Then we have which IO backend initialization. What does it do? I think even here we use virtual range, because see, this is the virtual range that we use, and the virtual range is mapped to the physical range. As the physical range though. Yeah, physical range is just identity mapped. I think that's how we did it. Yeah, so we just zero out the upper bits and we get the physical address. The let's say the virtual address was just FFF like 000 here. Then the physical address is just zero these upper bits and keep the other bits as it is. And that is what we do here. So this is also not an issue. I'm starting to wonder, maybe we'll have to run it and see where we've got stopped. I think we stopped at sys, right? No, we stopped within the kernel. So yeah. And then we have the kmalloc, and we have block write and block read, or about block write and block read. I think this is also using the virtual address, so this is also fine. Other than that, there's nothing much. We simply enable interrupts after that and we jump into the kernel. Here we just we jump into the user process. We initialize the user process and we set that as the initial task for the scheduler and we jump into it. That is all we do. I guess now we have to run it and see where we are getting stopped. I don't remember where we stopped actually, because looks like if I start from there, almost everywhere we seem to be using the proper virtual address whenever we try to access something, and we don't actually use the physical address. So where exactly are we getting the faults? That is what we will need to confirm now. Hi, what's up? Nothing much. Still debugging. Why is it taking this much long? Let's just kill all camo. Let's run it again. Why do I? Okay, I think we stopped. Now if we Fars just means that we are looking for any page faults, and we do have a page fault at address 800,700. Okay, I just remembered it. Yes. My MMU unit uses these addresses. See, we have we have lots of base address actually, and every address is physical. And why should I not just simply change it to virtual? Because these are table entries. So we have the MMU in it, and we have three different levels of tables based on the setup. No, I'm currently working on the block layer, so for file system, and currently I'm trying to test if my block layer is working from the user process. So I have added a syscall inside the user process, and it's just writes. It's a simple syscall. Where the fuck is that? Yep. If we come to my sys, so this is my user process. All I do is just write a small char buffer and call syswrites with that. And if I go into my syswrites, it's just going to call the interrupt. So we put the number, which is 64 for writes, and we interrupt. And then we should be jumping into our handler, which is this, I guess. Yeah, actually we are supposed to jump into the exception handler, which is inside the vector table. We should be reaching here, this code. No, EL0 sync entry. Yeah, we come from EL0 and we check if it's a syscall just by confirming if the bit is 15. If it is 15, then it is a syscall. We jump into syscall dispatcher, and syscall dispatcher is just this. Is it? Yeah. Here we take the syscall number, and if it is 64, we just write syscall is called, and we call block writes. This is the one that I have actually implemented, and I want to test with multiple user process so that I can confirm that there's no race. And yeah, previously I also added a spin lock to it so that even if multiple user process try to write to same things, it should work just fine. Now the issue is that the moment I come from EL0, which is my user process, into EL1, my table entries are not there, and the issue is just that all my kernel code, some of my kernel code is using address range 8000, and if I use address range that does not have the upper bit set, that means the MMU unit will just directly use the table of EL0 and not table of EL1, and I get the page fault, as you can see, the address is 8007 and this address is a EL0 address. And if I try to access this within EL1 context, then MMU is going to use the EL0 table, and EL0 table won't have anything for this address. And that is what I have to fix. Initially, this was like a hack I did just to get it working, because when I started, I didn't want to uh, create separate things. So I filled up all my user tables with kernel entries too. So things were working. Now that I have a separate user process, I cannot have that, because my user process has to properly have its own table entries, and my kernel table entries should properly be within the kernel address. So that's the only thing I have to fix now, but I have to fix it in a proper way. Yeah, I guess it must be almost the same. I'm not sure, but I haven't tried x64. I've only tried ARM. Yeah, so now what I have to do is that I have to figure out what parts of my kernel is actually using this 8000 range and fix them to have the upper bits. And one of the case is my MMU, and my MMU has multiple tables, and all those tables are trying to access this address, which is 8400, 8700 and stuff. And these are actually physical addresses, because MMU needs physical address. I think so. I don't know. I fucking forgot the whole thing. Let's just go through it again and see why we need it. Yes, we actually write into the table address. We have to update the physical address with the entries, because this is like my initial MMU unit. So I have the so ARM has multiple levels, and every level will hold a certain range of address. And in the 0th level, I have the entire kernel base, and in level 1 I probably have, I guess, 1 GB of range, and level 2 has, I guess, 4 KB. Yeah, level 2 has 4 KB, and all those tables are physical addresses. So how come I can convert that into FFF? I don't know. I have a table. And even to add, let's say I have a UART that is in range 9000, I need to add table entries for my kernel too. So whenever I where's my UART? So yeah, whenever I reach this address will be converted into 9000 something, and for that I have the entry here. Where's my UART entry? It must be here. Yeah, it's here. So 8200 is mapped to 9000. 9000 something is the actual physical memory mapped address of UART, and I need to add an entry for this address mapped to this in L2 table, and L2 table on its own is a physical address and it is 8680060, and this is the issue currently. When I call my kmalloc, let's say it allocates some memory, and it has to add table entries for those for that newly allocated memory. So it will try to write to this base address which is 8700. Now I'm wondering, is it even possible to, maybe then I have to put my tables somewhere else. Maybe that's the only way. Maybe I have to put my tables inside FFFF, which is the actual physical range. Not really. Or if I just add my whenever I want to write to that table, I will write to the virtual address and it will go and it will be put into the physical address. But whenever I reference it, I just use my actual physical address. Yeah, that should work. So here, whenever I call set table entry, I need to pass a physical address, and that I mean, currently I'm passing the physical address, but instead I have to pass a virtual address, but that virtual address should be mapped to the yeah, have fun, bye. And the physical address should actually, the virtual address should actually have a mapping to the physical address. Okay, how can I do that? Let's see. Looks like I already have a kernel base. Maybe these are all also already allocated. MMU init is fine because at this point MMU is not even enabled, so I can write or read to anything with at this point of time. Maybe I have to check from kmalloc. I am trying to do something. Where's my kmalloc? Okay, here's my kmalloc, and I think this is the map pageable entry. Here, let's say we access L1 create L2 table, L1 table, and This is a one-time operation adding my L2 table within the L1 base. Even this operation will fail if I call it within my, after I come into my come from EL0 to EL1, because even 8400 has no value in my EL0. I think whenever I make a table descriptor, or whenever I make a table descriptor and the page table entry, I have to actually pass the physical address. But when I set the entry, I can just pass the virtual address. I think that is what I have to do. Yeah, when I make this table descriptor with a L3 address, I think that's the only change that is needed. This L3 block must already be a FFF value. I don't know. I think so. We can try that. L2 writable, and what we want is add FFF in the front of it. So I just put 0. Yeah, 0x FFFF, and keep the rest as it is. One, two, three, four. 1, 2, 3, 4. 1, 2, 3, 4. And if I R it, if I R this with this, then the upper bits will be FFF. And I can use current L2 writable to set the entry. Let's see if it works or not, first of all. Let's kill this. Remove this. And then let's start over again. Let's see how it goes. See, we have a L3 index now. I think it will work now. We just have to fix the L3 index. L2 index is fixed. If we check the faults, yeah, now the fault is at some address. I think this is the address that this L3 table addresses. So what I have to do is that whenever we calculate the L3 address, which will be a physical address, for this L3 address too, I need to have a writable, and it's just going to be event 64 L3 table address writable, and it's just simply going to take 0x FFFF 1 2 3 4 1 2 3 4 1 2 3 4. Okay, and it will R it with L3 table address. Now we can use, whenever we make the descriptor, we can use the actual physical address, but when we write to it, when we actually write to it, we have to use L3 table address writable. I think it should be enough. I don't know, let's see. Let's see. We fucked up. L3 index is not working. Why? What did we do? Now we have a L3 address which is calculated based on L2 index, and we, okay, so maybe we need we try to reach this. Yeah, we have converted it properly now, but when we try to reach this address does not have a page table entry. So first of all, we need to add this entire range into the page tables. This entire range should be first of all identity mapped. But it's a physical address. Why do I have to map it? It's a physical address. It's a physical range of 512 into indices. Now I have it's a physical range, but from my kernel context, I should only reach it through a virtual address so that I can write to it. But when I do that, I get a fault for that virtual address. So now I'm fucking confused. If I'm gonna just add every entry as identity mapped from this, okay, so this is the table. So table needs to be always alive. That makes sense. It's not a user controllable location. It's the table's table entry. So what we have to do is that inside MMU init, I guess we have to call allocate identity mapping for L2 block memory start. because I can't do this here, because here I can't write two page tables directly. So I need a page table to reach the page table. So I have to do it within, before I enable MMU, that is within MMU init. Okay, that's fine, I can do that. Yeah, all I have to do is that take this memory location, create a how many indices are possible? Maximum of total. Well, let's just allocate 1 GB for it. And it's 4, maybe probably it's L1 entry. Maybe. Okay. Okay, let's go into my MMU init. Here, let's add an entry around here. So we calculate L3 table address. And we add a L2 index for this address. How do we add it? Let's put L2. Let's just fucking copy this whole thing. We want entry for the physical address mapped to the virtual address mapped to the physical address. So we also need the virtual address part. Where's the fucking virtual address? It must be here. Copy this line, we come here, we paste it, map it, and we want to we need an entry for this writable, which is a virtual address, which is mapped to L3 address, and the L2 index should actually be 0, because we need the 0th index. Starting from 0th index, we need 1 GB to be allocated. So let's write an warning here to do what happens if we someday allocate more than 1 GB, so we don't have table entries for the L3 table on its own. Let's also write a warning there. L3 table on its own needs to have the table entries which is added in MMU init, and currently it only holds 1 GB of 1 GB of pages, let's say 1 GB, just 1 GB. Now if we try it, let's see what happens. It did not change. Why? I just fucking added it to L2 entry. Maybe do you need a L1 entry too? Oh fucking hell. I think I need an L1 entry. I don't know. I'm a bit confused here currently. What exactly do we need? We have an address range, and that address range should be inside the table. Okay, that's fine. So inside the table, as in does it need a L1 index? First of all, what is the error? We will know that better, because the error is just going to give the table level where their fault is occurring. So now if we run it, and I guess we are stuck there, and if we run it, we get this. Let's just copy this. I think 4 means that it is L1 index. It's L2 index. I don't know, we'll try. This is the error code, 4. So 4 means level 1 faults. So I need a table entry in level 1 too, because right now I only added a table entry for level 2 for this address. So I need a level 1 entry first of all, because I added the L2 entry, but the actual fault is in level 1. Translation fault is level 1. So I need L1 entry. Okay, fine. So I need a L1 index entry for that, and then I need a new L2 table now, because I need a L2 table, and I have to use that L2 table again. Fuck. Let's create a new L2 table. No. What the fuck? Oh, fucking hell. Okay. Okay, now I need a L1 entry. So if I need a L1 entry, I also need a L2 table to put the L2 entries, because I cannot use the existing L2 table, because the existing L2 table does not even cover this range. So I add a new table into L1 and update that L2 table again. This is what I have to do. So let's create a new table, and let's name it as We do have a L2 table here. Let's just create a new table. Kmalloc tables on its own. Malloc table entries. Kmalloc L3 table entries needs a table on its own. Okay, 6 is used, 7 is used, let's use 8. Hopefully nobody else took that. I don't know. This looks like we are using 8000 here. Oh, fuck me. Maybe we'll put 3 here, 4 here, 5 here, and 6 here. Will it work? Well, we'll try. Nothing wrong in trying. It's not gonna do anything. I'll just try. Hopefully everything is dynamically allocated and I haven't hard-coded anything there. If I did hard-code anything, then it will just fucking fail. Okay, probably I did hard-code something. No. I just have to add the entry first of all. Okay, we have changed these things. Now L2 far base physical address for L3 entries. What the fuck is this naming? Next time I'll come here and I'll be wondering what the fuck is this. Well, I guess it's his problem, not mine. Now I just get into MMU init and add a L1 index. Just copy it, paste it. I need a L1 index for I need a L1 index for my L3 table. This if you put 2, okay, that's good. Where's my new line? I'll just put it in the top. And index is 0. And now I can use L3 table address because I have to give the No, and writable. I need to give the virtual address. For this virtual address in L1 index, we need to point to L2 table, which is L2 base for L3. Now we have a L1 entry for this address, which is pointing to a new L2 table. Now all we have to do is that update the L2 entry to use that new L2 table. So now within the L2 table, we have a L3 address and L3 block. Oh, fuck me. Now if we fucking kill it and run it. What? What the fuck? What the fuck did I do? Okay. I just missed some quotation. Nothing much. Nothing serious. But which line has the fucking out here? I got scared that I fucked up big time. I guess I fucked up big time because it's not even working. It does not even start. Why? Let's see. I think the issue is because I created a L2 table. What the fuck did I do? I have a L3 table and this address, for some reason I get a L1 table error. And if that address comes in, we are going to go here. And I think we are overlapping a little bit. But if it's actually overlapping, that's why I only added L2 entry. Then you said you don't have a L2, L1 table. That's why I added the L1 table. Now you are saying that someone else is. It's not possible someone else to access it. If it was someone else, then we should have gotten error previously. So maybe I'm just not thinking it correctly. Thinking about it correctly. Okay, what do I do? We have a L1 index. If I don't want this L1 index, I believe we already have a L1 entry for it. Now it's 4-6. Looks like L2 entry. I think it's L2. Yeah, it's a fault at L2. Because I have this new entry, now these addresses are getting into this location. Maybe I can just add the index here. Okay, we'll try one stupid thing and then we'll give up. And this hack is going to fuck me up sometime in future, but until that time, I think maybe it might work. All I'm gonna do is that I'm going to recalculate it, but for indices for int I equals 1, I less than 20, because I think we only can allocate up to 20, and I plus plus, I just put this whole thing inside it, and the index here. Okay. For every index, I should only allocate once. Sometimes I might reallocate the same location in this loop. So it's better to, first of all, let's confirm if it's only 20, and then I can add that part. Go to app. I think, yeah, it's only 20. You can only have maximum of 20. So even here, when I try to, okay, this is L2 index, so it can be anything. That's sad. Well, let me just put that test 20. We don't have mem sets. Let's just put 0. Uninitialized location. So what if something is there? There's no 0 initialization possible. Okay. And first of all, I need to put a for into. This is why sometimes C feels bad, because we don't have enough things. We might have to write the same things 1,000 times. Be nice to have a good library or standard library. Okay, now we have all those values set to 0. Now we can check if it is 0. If I test of I equals not equal to 0, then we just continue. If not, we finally we add I equal to 1. Well, this is a stupid thing. Well, we'll try. First of all, we have to fix the errors. And looks like we cannot simply have 0 initialized to it. So we'll put it as empty. And we don't even have an initial. As soon as we get into it, we get an error. And this location is being tried and we get an error. Fuck it. Let's just write to do we have a L3 table physical range that will be used by Kernel, and it needs virtual address. So we need to fill it up here, but looks like we are overlapping a lot of stuff. Let's go back to original setup, and original setup is it's 2 and it's 4 and it's 6 and it is 7 Let's make it 9. And we don't have it working. And let's also remove some junk that we just added, because I think it does not matter. And we have address table, and let's just add let's just add the L3, and we are going to add it within L3 base, L2 physical base, and we don't need this L1 entry. Okay, now we have simplified it to a error that we got previously, and here we just get L2. And now if we try it, we get an L1 false for this entry. Okay, let's start from here tomorrow and see if we can figure it out. Okay, thank you guys. I'll see you tomorrow. Today we just managed to, I guess, at least understand the problem a little better. Bye bye.